Hi, I'm Francis Saturn M. Mendiola, and I will be discussing to you now the transverse waves and harmonics. The best thing to illustrate transverse waves and harmonics is we have here an electric guitar. Now, harmonics in music are notes which are produced in a special way. They are produced as part of the harmonic series. Now, in physics, a harmonic is a wave which is added to the basic fundamental of wave. Let's dive into first to the theory of how transverse waves and harmonics. Today we'll be talking about standing waves. What exactly are standing waves and how it will be created? Let's say we have a string that is attached to two fixed ends, and we apply a tension force, and if we pull the string and release it, it will create a standing wave pattern. A pattern that will look like this. We can also get a pattern that look like this. Now, granted, because it is vibrating so fast, might appear to be something like this, where the second one also will, if it is vibrating so fast, will also look like this. It is called a standing wave because it appears that the wave is not moving in the x direction. Now, let's talk about the different shapes of standing waves. If we have one standing wave here, n is equal to 1. If we have a pattern of two standing waves, n is equal to 2. If we get three standing waves, n is equal to 3. So, in the illustration of the shapes, even though it appears that they have different lengths, but technically the length there is the same. So this is the length of the string for the N1, and in N2 this is also equal to the length of the string, and also for the N3. So the best illustration that I can give you for the N1, I have here a coil spring. We vibrate it in a simple manner like this one. So this will be the N1, where the number of the loop is 1. If we add a little bit of speed on the spring, so it will create the two loop. Have you observed the two loops? I don't know if I can make 3. No, I cannot. Now let's proceed. The wavelength and L is associated with this equation, one half of the wavelength. This is one full cycle of the wavelength. So the length of the two standing waves in the N2 is equal to the wavelength. So the subscript 2 there corresponds to the N value. So for the next one, we have three standing waves. L is equal to 3/2 times the wave. The equations L is equal to N times the wavelength and divided by 2. So L is equal to N times the wavelength divided by 2. Now if we rearrange the equation solving the wavelength, it will be wavelength is equal to 2 times L divided by the N, which is the number of standing waves. Now all of these standing waves, they occur in a natural resonant frequency of the string. If we use a different material, affect
the standing waves that will produce. Let's say that L, the length of the string is 0.5, and the frequency of the first standing wave pattern, let's say, is 100 Hertz. Other frequencies like the next frequency F2 and F3 are all multiples of the fundamental frequency F1. F2, which corresponds to the N2, the second wave pattern, is equal to 200 Hertz. This is known as the second harmonic. The F3 is the third harmonic. It has 300 Hertz. F2 and F3 and above, anything beyond that, is called as the overtone. So as you can see, as the number of standing waves increases, the frequency increases. So the frequency is proportional to the n value. The frequency Fn is simply n times F1, or fundamental frequency. The wavelength is 2L over n. So 2 times 0.5, which is 1. And when n is 1, that is, the wavelength is going to be 1. So the wavelength that corresponds to the first standing wave pattern is 1 meter. So the next one, we have 2 standing waves. So notice that the frequency increases in the following frequency pattern. So originally, for the F1, the wavelength is 1 meter. Now it'll be 1/2 a meter for the F2. We triple the n value for the n value, the wavelength, the frequency is increased a factor of 3. So therefore, the wavelength is decreased by also a factor of 3. So it'll be a 1/3 of the original value. So lambda 3 will be 1/3 of a meter.
So in this equation, we can now find the location of the harmonic sounds of the guitar. For the fundamental harmonics, or the F1, we cannot play that actually because in our calculation, the harmonics can be found in the times to the length of the strings of the guitar. The length of the string of the guitar is actually from here, the neck. These strings here are not included. From here up to the bridge of the guitar. If we find the harmonics here, that is half of the second harmonics, which is called also as the overtone. Okay? The overtone in music. So that is a half of the length of the strings. So here, this is the half of the string, the location. Now, surprisingly, this area here is the repetition of the notes from the open strings. So for example, the open string here is the E. If you count the notes here from the open E up to here, you count it E, open, and F, F sharp, G, G sharp, A sharp, B, C, C sharp, D, D sharp, and then the E. So it is a full cycle of notes. The location of the harmonics, the second harmonics, is also the location of the open strings here. If I play the harmonics now, by the way, harmonics is also a technique in guitar where the guitarist makes a sound of a high pitch. They sometimes call it a cry, so like this one. Oh, have you heard that? It's like a cry. So if you pluck it that in this way, by adding a note on the middle of the length of the string of the guitar, that is the second harmonics. Now the third harmonics is located in the 1/3 of the length of the guitars here. So this will be the third, 1, 2, and 3, and this is the 1/3 here. If you count again the notes here, so from E, F, F sharp, G, G sharp A sharp B, C, D, D sharp, E. So here is also the location of the third harmonics. If you want to listen to the third harmonics, the technique there is just by pinching the location of the harmonics at the edge of this, not really stopping the string, but like touching lightly. So it needs a practice actually. So let's proceed to the discussion. More theory.
So whenever n increases, that is the number of standing wave, the wavelength decreases and the frequency increases. So the fundamental frequency Fn is equal to n of the fundamental frequency multiplied. Now if we know the speed of the wave and the length of the string, we can find the harmonic. If we want to find the fundamental harmonic, which n is equal to 1, for the second harmonic, which is the first overtone, n is equal to 2, and the third harmonic, which is the second overtone, n is equal to 3. The wave speed is equal to lambda, or the wavelength, times the frequency. And if we need to find the wavelength of any standing wave pattern, that is 2L divided by n. Now we need to find the length of the string, which we have to find the harmonics. It'll be L is equal to n times the wavelength divided by 2. For the guitar equation, we'll be calculating the velocity, the speed of the wave, that will be equal to the square root of the tension force over the density, the string density, which is the mass over the length of the string.
In the guitar equation, the speed of the string equal to the square root of the tension over the string density. The application with as you see a guitar string with respect to their mass, the number 1 here, or the high E, has lighter mass compared to the upper strings here. So as you observe, the smaller ones creates a much higher pitches and frequency, and then as it increases the mass, it will have a lower frequency. The length also will affect the tones of the guitar. This is called as the whammy bar. The whammy bar here is letting the player to decrease the length of the string and increase the length of the string. Like this one, I want to decrease the length of the strings. As you observe the tones going low, and if I increases the length of the strings by pulling it, it will create a higher frequency. So in some guitar techniques there, combining the techniques in the harmonics, which is the highest pitch possible, and also increasing the string, will create a very loud noise, like a cry. Like that one. The tension of the string here is also could affect because of the whammy bar. If you push it, lowering the length and also lowering the tension of the guitar. So, that is how harmonics and the guitar equation works in an actual guitar instrument.